Good afternoon. I would like to share with you some applications on the Fourier transform group for optics. And I will be doing these applications with diffraction patterns involving circular and different number of slits. So it's a little bit overview. I'm gonna talk a little bit, just a little bit, since you guys already saw the videos. But I'll give you a little bit of a refresher about the math and the theory that goes behind taking a Fourier transform. I'll also be discussing some MATLAB results dealing with the circular aperture, and then some MATLAB results with the slit apertures, and then I'll walk you through what I had to do to set up experimentally. I actually really wanted to build something. That's why it took me a while. And I'll be talking in there about the materials and apparatus as well. And then at the end, I'll just give you guys the experimental results, and then we'll have a discussion at the end. So a little bit of background. I don't know if you guys remember, but these are the two different versions. You can either take the inverse Fourier transform, which will get you in terms of like spatial, or you could take the Fourier transform, which will take you in terms of frequency. And that's kind of just telling you how many times it's been at that point in the past. How often it's at that point in the past is pretty much what the frequency domain. It's a little weird. That's why we get a lot of computers to do the work for us. However, to put it simple, Fourier transform of an image will pretty much just taking Fourier transform of an image will end up giving you the diffraction pattern of that image. For example, if you take the Fourier transform of a slit, like I discussed in the videos earlier, you end up with the sinh function. The sine of x similar. And if you take the Fourier transform of a circle, you end up with the sinh, except that it's rotated on every way, so it kind of looks like kind of like you've seen this a lot probably in like physics books, textbooks, where they drop a little water in the droplet of water, and then it looks like it bounces up, and it looks really Gaussian sort of. So this is what we have for the circular aperture. And I don't know if you guys remember, the bigger you make the image, the less of a diffraction we're gonna get. So we needed to make this aperture really small. This is what we did for MATLAB. You guys can go ahead and read the comments if you guys have a little bit more questions. But I did use the built-in function, the FF2, the FFT shift. And that's just pretty much just the built-in function, instead of having to do this all over again for every single time. I just kind of use the built-in. MATLAB has a built-in function that does the Fourier transform of whatever image or whatever signal you're getting into. And yeah, as we expected some sinusoidal looking diffraction. So at the lower points, that's where no intensity or lower intensity is seen, and at the higher lit points, that's where higher intensity is shown. And these are for the different amount of slits. And yeah, you guys can go ahead and see the comment. I just kind of did comments on the last one, but you guys can go ahead and see the different number of slits. So the single slit, and I actually did this one. These are not perfect cubic rectangular slits. These are a little elliptical, but elliptical enough to make it look like a rectangular slit. And then when I pass light through here, it ends up looking like this. And the most intense is around 2,500, around there. And then when I pass it to two slits, what happens when I change the number of slits? The number of fringes in between changes. So now we can see we have a law, like we have actual number of fringes, and the intensity in the middle, the peak intensity also increased, which is something that we would expect. And then bam, we add another slit in between. You guys see that there's a little bit of distortion because it's not a perfect rectangle. And the inputs stay at the same incoming intensity, but the outputs, they keep increasing. And bam, more number. You guys can't see it, but there's actually an increased number of slits, a lot more in there. And yeah, so it can only at least on theoretically works out. So let's see how we did with the experimental results. So this was a low budget. So this is what I used for my setup. It was a regular laser pointer from Safeway for cats, and just kind of mounted it on top of these PVC pipes that I had. And then there was a cracked mirror that I used to reflect the light. And so in order to do this, we needed to make sure that the light was coherent, like we've seen in class, and it also we need to make sure that the light is not super divergent, which is why I had to use some glasses, positive and negative lenses to focus in and out the light. And these here are the bottles. They're actually bottles of I think I don't know, some tea, a tea, and I actually used that same not bottle, can to walk the beam over and make sure that it was at the same height out throughout. Just, obviously the table is flat. And here's my circular aperture made with the really small needle. And then here are our slits, different number of slits, single slit, double slit, triple slit. And I had to do this with the razor blade really lately. First, initially, it was this was my mount. But then since the holes in here, or anytime I made slits, it was not perfectly. The diffraction pattern was not super neatly. And these are my experimental results. So when I pass the light through here, so first initially the light looks like this. The beam without anything looks like this. I pass it through here. And then this is the incoming beam that I catch with my camera. And then if I take a picture of the screen, it looks like that. And ta-da, we have our diffraction pattern. And that's pretty cool. And then let's do the single slit and pass it through this guy. This one passes to this guy. And then we end up having, these are our kind of lobes. Similar, I had to take two pictures to like verify. But yeah, look, cinch pattern. And then we pass it to the double slit. And then the double slit was the one that gave me the most issue. I don't know if you guys can see. There's like a little cut at the bottom, but this was the best one I did so far. So it's not a precise rectangle. It's more like a heart. But yeah, you do, however, see that the fringes in between the original cinch pattern. And then we do triple slit. I was only able to get one picture because it's really hard to align everything. But yeah, we do triple slit, bam, number of fringes increases and it gets even like brighter. So um in discussion, I guess you could say that, like we talked about earlier, the Fourier transform of an image will result in the diffraction pattern of that image. And what we can do from this, not only can we just have fun with lasers and play around with light, but we can also like throw light inside a vessel that we know how the aperture looks like and we know how the diffraction pattern should look like. But if it comes out anything different than that, we know that there's something inside it. For example, we can go ahead and scan my bone, or pass me through an aperture and then pass some light through it. And then if light bounces in a way that it shouldn't, and the diffraction pattern is something that is unexpected, that means that there's something unexpected inside my body. For example, like there may be cancers, or there may be like some benign tumors growing inside there. But yeah, we can use this for medical, we can use this for defense, we can use this for a lot of things. So I recommend you guys to go watch the videos again. And thank you for watching.